Welcome to today's Ascendo Reliability webinar. And today's topic came from a suggestion last month from one of the participants, one of the attendees, and I appreciate that. And just before we hit record, the few folks that were here a little bit early, I asked for some ideas, and I got a couple of ideas there. If you see or hear or are thinking of a topic you'd like to have a webinar on, at least get mine, or I might invite somebody that knows the topic better. Just drop it in the chat and I'll keep an eye on that. And I'm always looking for good ideas on that realm. But today is on capacitors, and we're going to talk about two different kinds of capacitors: multi-layer ceramic capacitors, MLCC, and also the aluminum electrolytic capacitors. Not the two, the headlines are from NVIDIA with their fancy new GPUs, and there's big chipsets they have and stuff like that. And capacitors have rarely, if ever, made the headlines in national news or in financial news or anything like that. But we'll talk about some of the ways that it has an impact and some of the insights and ideas that may help you as you approach this relatively common component. And they're simple. They are actually quite simple components. They have been around since capacitance was basically discovered. It was basically creating two plates, parallel plates, that have a dielectric between them. And it would create a phenomenon in electronics that we call capacitance. It's some stored energy of some sort, and it could do it in a variety of different ways and all kinds of different purposes for it. Yet it is a relatively simple device. It really is just parallel plates with a dielectric between it. There's a cathode and anode and a dielectric. And I think I have a drawing of one of those to examine that a bit closer. They're amazingly common. Capacitors are pretty much on every single circuit board that I've ever seen or ever been aware of. They are, I had one electrical engineer describe it as, well, at this point, I take out the capacitor salt and pepper shaker and just cover the board with it, because they were used for dampening downstream currents and fluctuations. They were used as ways to protect from ESD. They were used in circuits like resistor capacitor circuits for different purposes of modulating signaling and modulating inputs and outputs, and that's just scratching the surface of all of the ways that we use capacitors in electronics. And even in big solar system arrays, there's an inverter. There's inverters in your car that convert energy from one kind of energy to another to do all this stuff. And sometimes those capacitors, especially the ones I saw in inverters, they're like the size of a loaf of bread. They're good, hefty chunks of capacitance, and they made dozens of them inside this chamber, and having to do what they need to do in order for us to convert DC power to AC power, for example, on those things. And so there pretty much anything that we plug in or has got a battery or has got any kind of electronics, whether it's on a fixed circuit board or a flexible circuit board, there's more than likely capacitors. They're amazingly common. And the funny thing is, even though that we've had this technology for over 100 years, probably closer to 150 years, they still fail. And some of them wear out. The electrolytic capacitors do over time. Multi-layer ceramics, they fail for all kinds of reasons. And we'll get into both of those in some more detail. But it's one of those things I say often in our field is that It's what keeps us in business. We find new ways to cause failures in capacitors over and over again. And it's being aware of capacitors and how they're constructed and what types of failures should be expected or could be avoided. I should probably spin it a bit more positively. Helps us then to create designs and create products and do failure analysis a whole lot more efficiently. And so we'll take a look at a handful of things. Hopefully, it gives you a couple of ideas. And I'm quite sure some of this stuff you're already aware of or have seen. So let me put it this way. Have you been involved with a system that it's because the capacitors failed that you had to do some failure analysis or had product returns or saw some anomalies or something like that? Have you seen any of those kinds of things? You know, take a look over at the chat window. Oh yeah, Sebastian. Oh, yeah. Um, and I see a note, another vote for the AI and reliability. Yeah, I might. I mentioned before the start, I'll have to see if I can find somebody that's a bit more versed in AI than I am, but we'll see how that goes. A couple of votes there. But years ago, I was talking to a friend of mine and colleague that worked at a failure analysis lab, and they worked with corporations and companies and groups of all kinds. There's an open failure analysis lab. And they said about a third of their cases that they were asked to do failure analysis on involved failed capacitors. Now, sometimes capacitors fail because they just fail on their own. They have a failure mechanism that takes charge and leads it to failure. And other times they're the victim. Yet capacitors do fail and they can cause all kinds of havoc on your boards, on your systems. At first, let's start with a couple of stories. And some of you, I recognize, may have heard a handful of these stories in one form or another over time. And some of you may have even lived through some of these. But, and I've listed at the bottom of the slides where I'm getting some of the references for these things. But this one I actually lived, and I didn't know it was in the media. It was in different trade journals and stuff like that, and or had this name of capacitor plague. But years ago, I was working at Hewlett Packard, and of course, it was a Friday afternoon. I get a phone call saying, "Hey, we've got these." Servers that we have capacitors on, electrolytic capacitors, and they're venting. And I'm like, well, they do that if there's, bad design or ripple current, all kinds of other things. We'll get into some of the details of how they would create excessive pressure inside the can. And he said, no, these are failing in our prototypes before they've been aged all long. And it's pretty, we check the ripple current, we check this, we check that. They're not being overheated, blah, blah, blah. They said, no, this is from the vendor, but we don't know why. And so we talked a little bit about what they could do. And there was a failure analysis lab close to them that was more of a chemistry FA lab. And I said, why don't we take a look at what's inside ones that haven't failed yet and see if there's something odd about how they're constructed. And it turned out that in the next week or so, I got 2 more phone calls from other organizations that were also having a very similar, very premature venting of these or getting bulging, as some noticed it, these electrolytic capacitors. And they weren't really large. They were maybe a 1/2 inch to 1 inch tall, maybe a 1/4 inch to 3/8 of an inch in diameter. So they weren't monster ones. Yet what happens when a capacitor bulges, or the little crosshairs that you see on top of these cans or little S shapes, those is a weakness in the can itself that allows it to vent. And vent is a euphemistic for explode, right? If you don't do it, pressure would build up and it would rupture that metal can. that aluminum can. But what was happening is things were bulging or they were venting, but it would simultaneously change the parametric properties of that capacitor. So instead of particular performance characteristics, those were changing. So there was something happening on the inside of this capacitor that one of the byproducts was that it would build up pressure on the internal part of the product and hence bulge, and eventually it would vent. And these were happening across their boards. They weren't just test devices. They weren't just ones that were stressing or anything like that. They were just kind of idling along and doing support for software development on all kinds of different places that this was happening. Well, what was going on, and there's lots of details of the episodes in the late 90s, early aughts that talks about this on the Wikipedia page. But basically, somebody, a chemist that was working in a Japanese manufacturer that designed and built capacitors, decided to go back to where they used to work, and they took a formula or the recipe for the electrolytic solution. But it was mistakenly, they had an error in the recipe when they copied it down. And so they went to the new site. They said, oh, we got this great formula. And it didn't have a element in the electrolytic solution that's called an oxygen scavenger. And what it basically does is it's a chemical that when oxygen is, and it's a byproduct of electrolytic capacitors operating, when it's cycling and powering up or powering down or doing its thing, because of the chemical reaction, some oxygen is released. And as that oxygen is released, it goes from a liquid to a gas, and hence creates a lot more volume, and it would create that internal pressure. In order to alleviate that, the capacitors designers add this element, and I know I looked it up, but it's something I can't spell, so I probably can't pronounce it anyway. But it was a chemical that then would sequester that gas and turn it back into a liquid. It would capture it, put it back into a molecule, basically, that would take a lot less volume. And part of the recipe is to put enough of the scavenger in it for the expected lifetime or useful life, or however we want to define it, how long they should last. So there's plenty of ability to capture the oxygen before something else causes this device to fail. Well, it turns out this person then decided to go create their own company making capacitors, and with the bad formula. And over time, there were millions of these capacitors being produced and shipped out. Now, I didn't know of the bigger story of how all of this was going on. I learned about it later. But inside the company, I got a couple of phone calls. What's going on? Well, let's understand why it's happening. And a basic understanding of how capacitors are made led us to do the chemical analysis. And sure enough, the elements that would typically gather up and sequester this oxygen was missing, or in very, very small amounts. And so the natural process of this capacitor working was going to lead to its premature failure. And so we basically then started testing, not any lot sampling or anything like that, but we worked with various vendors that we were working with so that we could understand if they had the scavenger type chemicals added to it or not, and if there was sufficient amounts in it or not. It turns out that there was like 4 or 5 companies altogether that were creating these faulty capacitors, and it was a little bit cheaper, but it was out there, and it apparently ran for almost 8 or 9 years while it was still available in the market. I ended up in knowing that it was related to at least the one vendor we were working with. And very quickly, the lawyers got involved and pretty much clamped down everything about what we knew or could talk about and all that good stuff. And I never did find out whatever happened with that. Our business at that point was, let's go find capacitor vendors that are good. And we did internal chemical testing to find out and to make that all work. And it affected, at one point, it was affecting about a third of our products. And because of our development process, very few, if any, that I know of, products got to the market with these capacitors in them. So if we hadn't done due diligence or paid attention to what was going on our circuit boards, it's very likely that a whole pile of, say, printers or servers would have been constructed and shipped. But we were able to catch it and then avoid introducing these faulty capacitors into our organization and into our customers, over to our customers. It's one of those things with suppliers is that you have to trust them. We can't afford to do burn-in testing and incoming inspection and all the other things that we've long ago stopped doing, because by and large, our vendors are pretty good and the components they make are pretty good, especially capacitors. It's been a long history of very good capacitors being made. Yet it's this, you got to trust them, but verify. And so we routinely started doing the chemical breakdown of what was in these things, and somewhat to the dismay of our vendors, saying, how do you know what should be in there? It says, well, it's pretty easy. This batch works, that batch doesn't, and the difference is what we're looking for. And oh, okay. And one even got indignant and says, you're not allowed to do that. Says, we have a chemistry lab. We can do it. So sometimes having the right tools and equipment available to you makes a big difference. Right. Another story, this one I know I've talked about in various ways and forms, but I'll try to flesh it out a little bit bigger, longer. But this is dealing with a multi-layer ceramic capacitor, the little chip capacitors that we see on just about every circuit board, and they're getting smaller and smaller every year. I think the smallest I dealt with when I was at Hewlett Packard 20 years ago was a 0204. It's a 2 millimeters by 4 millimeters, I think is the units of that, or is it mils? I don't remember. Now they're even smaller than that, much, much smaller. And some are quite a good sized piece, the size of your thumbnail kind of size. They can range all kinds of sizes, and they are a very, very useful component and have an appropriate amount of capacitance. They come in different grades and varieties and stuff like that, depending on what use you have. They're different price points and different capabilities and so on. So I used to work at the printer division, one of the printer divisions, and a good friend of mine, after I moved to corporate, basically, I was in a technical group that sat at headquarters, but we weren't actually in the chain of command to the CEO and all that good stuff without appropriate dozens of layers. But we were a technical center of folks that basically worked across the organization, providing education and lab services and research work and all kinds of weird stuff that we did. And I was working in a team that was creating or continuing the reliability effort at corporate. And so it was our design guidelines and all kinds of stuff like that. And for a colleague of mine from where I used to work called again on a Friday afternoon, and he was almost whispering, which I thought was very odd. And he said, his first thing was, you have to realize that I'm not allowed to talk to you. I'm like, is this guy in jail or what's going on? What's happening? And he quickly explained that they had a product in the field that had a visual thermal event. And I thought, what? He says, well, we're not allowed to use that 4-letter word that starts with F. And it's like, okay, visual thermal event. Okay, well, that's not good. That's not what our products are supposed to do. And he goes, yeah, exactly. So we've isolated it to a multi-layer ceramic capacitor that is getting very, very hot and is igniting the circuit board around it. And that's really hot. And he knew all these details. They were able to replicate it. And he said, but I'm not allowed to call the supplier to ask how does this happen? Because we're not allowed to release any information about what's happening. And the lawyers have already gotten involved and locked them all down. They said, this is a very big deal. This is one of our major product lines, and we need to understand it whether we do a recall or not. And it's $100 million question. I said, okay, then why are you calling me? What can I do? You sound like you got a pretty good handle on it. He says, but we need to know, is this going to happen to every capacitor that is on these products that's already been shipped? Or is it, what's the probability of it happening? And depending on if it's very common, we'll do a recall. If it's over some threshold, we'll do a recall. But they need information as to how likely is this to happen. And you're like, I have no idea. He says, that's why I want to call the supplier and talk to their technical folks. Oh, okay. Well, let me try that. And because I was sitting in Palo Alto, I could call them and say, hi, this is Fred. I'm from corporate. And I got connected right straight to their senior technical folks and described what we were seeing and said, how is this possible? How is it that this multi-layer ceramic capacitor looks and feels and performs like a capacitor, and then it doesn't, and it turns into a ceramic heater? I mean, white hot ceramic heater. And he goes, yeah, that can happen. Like, and you knew about this? And then we went into some of the details and some of the chemistry of what's going on and so on. But what, in a nutshell, what's happening is there is a crack. And we'll talk about where cracks come from and some of the tell signs of different styles of cracks that occur in a couple minutes. But the idea is that there's a crack, there's an initiation of a crack. And then a few power cycles or few thermal cycles, that crack will propagate. And once it goes through a couple of layers of the metallization between the plates of ceramic, that will create a path that allows metal ions to traverse between those two polarities. The plates are oppositely polarized. There's anode and cathodes on those. And so there's well, I'm drawing a blank on the name of it. There's electromagnetic force is probably not the right word. I know somebody will come up with it. But the idea is that you'll get a few metal ions into that crack between the two plates, and it'll create a small amount of conductivity. And the electrons go, oh, I can go this way, take a shortcut. And doing so, they create heat. Now, in general, when a capacitor cracks and this happens, the vast majority of the times, that capacitor it essentially just blows up. It snaps, it breaks completely apart, and it becomes a completely open circuit. There's no capacitance there anymore at all. They just, with the right current and the amount of power that's available on most boards, that crack will propagate to a point. It'll become conductive between the plates. It'll be a dead short circuit. They'll just explode. The heat buildup is very fast, and ceramic is very fragile. It's glass, And that heat differential then causes it to fail. Under specific circumstances, if the current is not too fast, it's not too, doesn't create an immense amount of heat all at once, it can create just enough heat to change the barium titanate, if I remember the full name of it correctly, and it strips off some of the oxygen from the molecules in that, and it turns it into a relatively decent, yeah, that's it. Like, thanks, David. Electrochemical migration. But there's an electronics force that is electric field. That's what I was looking for. But thanks. The idea is that the barium titanate, with the appropriate amount of heat, will strip off some of the oxygen. If I get that right, I don't think it's adding oxygen, but it's stripping off an element of the makeup of that chemical, that ceramic, converting it into a relatively decent ceramic heater. Now, that only occurs right along the surface of the crack. And as that occurs, it's able to carry more heat. And more heat then goes into the bulk of the ceramic all around that crack. And over time, you get a really good conductor so that it can handle all of the current that's being applied to it. And it then heats up to white hot and causes other things to ignite. The likelihood of that was actually pretty rare. And it happened to have, 4 or 5 different things that had to happen to make it work. And starting with a crack and a particular type of circuitry, and there was like 4 or 5 other things that were involved. So we were able to work out with back of the envelope type calculations that this was rare. And so fed that back to the organization, and we got a letter back from the program manager saying, thanks for the information. This helped us to make the appropriate decision for this $100 million decision. And so my boss was ecstatic about that because I actually got proof that I was instrumental in a major decision. And so added all kinds of value. It took 2 weeks to do the phone calls, check in with some chemists, do the research on how in the world, what's the activation energy to change this ceramic into a conductor, and so on and so on. Fed that all back to them. They made their decision. They moved on. Now, in the next story, I'll talk a little bit more about the next step in this exact same scenario, because I went and visited the manufacturer. Yeah, Carl's talking about you got to prevent cracks, and that's really a perfect segue into this story. So the question I got after they made their decision is, well, where are these cracks coming from? Now, I was surprised they took this long to sort that out, but they said, and at that point, I was very well versed in circuit manufacturing, or the board stuffing facilities that would take all the components in our circuit boards and produce them for us. They had all these pick and place equipment and so on. And at the time, I was working across the world, basically assessing different vendors that provided circuit board manufacturing. And so they said, you know what you should be looking for. Can you go check them out for us? So I flew down to Mexico, and they knew I was coming. And my host drove me up to the factory, which was relatively new. It was amazing. It was a complete side story. They gave me a quick tour of the building, and there was this space it was probably 2 football fields in size. It was a massive building. And they were putting the floor down on one end of the flooring over the concrete. They were putting down this electrostatic discharge, prevention type stuff, conductive flooring on one end of the room. And they were forklifting in equipment to set up a production line. So soldering and pick and place and all that good stuff. And there's about a dozen machines in the line that gets put up. And they were still in crates. And they said, by this afternoon, we'll run a test line. By tomorrow, we'll be running production. And they were going to put 40 lines in that room. And it would take them about 2 weeks to do it. The rate of their ability to manufacture buildings and put this equipment in and get it into production state was absolutely phenomenal. Now, as you can imagine, they were hiring as fast as they could. And there was another rival company right across the street. And their biggest problem was they train somebody up and they get a pay raise going across the street. So there was a lot of labor competition. And I commented when I got there, it says, "Oh, I saw you have this bus pulled up and all these people are getting off. That's cool. You're running buses out so they don't, save on parking, or is this the service for your workforce or stuff like that?" It goes, "Oh, no. That was from the unemployment office in town, and people that were interested in working in the factory, we put them on the bus and bring them in." And I said, "Oh, that's cool." And they said, "Oh, we do lots of training. We make sure they're okay. We, make sure they're well qualified before they get on the floor and all that other stuff." Well, I saw one young man get off the bus that just had I think it was an AC/DC rock and roll band T-shirt, and I just recognized that and commented that, "Oh, that's cool. You're busing folks in. And he said, "No, these are all new people." Okay, so the quality team that I met then wanted to show me all of their what they should be doing, blah blah blah. I said, "Let's go walk the floor." And lo and behold, there was the kid with the ACDC T-shirt on. He was on the production line less than an hour after being hired and depaneling boards. And for those that are familiar with depaneling, is when we make circuit boards, they're usually in a big panel, and you might have like a 2-inch by 4-inch board that is the final product, and there might be 100 of them on this panel. And they're all kind of kept in place by these little tabs that kind of make a network of stuff to hold everything in place. And to finish the circuit board, we have to take them out of that panel. And it's called depaneling for obvious reasons. And there's lots of different techniques and methods for doing that. But one of the easiest, most flexible ways that many manufacturers use is you just do it manually. They're called break-off tabs for a reason, because you can physically break them off. The downside is that if you don't keep the circuit board flat, you don't want to bend a circuit board. If you've ever done that, you can hear the cracking that occurs. And lo and behold, this young guy had less than an hour of training, was said, "Here, do this." They probably showed him once or twice. They may have showed him the way to do it properly, but he had no supervision until I got there. And he would grab the electrolytic capacitors on the ends of the two boards he was breaking apart, and in the air, bend them so that they would break the tabs. And you could see the arc in the boards, and from 10 feet away, you could hear the cracking, which was probably the fiberglass board, but also the ceramic capacitors. And lo and behold, I grabbed one of those boards and said, "Let's go do a scanning electron microscope, a CSAM on this thing, and find out if there's a crack in it." And sure, all of the capacitors that were aligned parallel to the long edge of the boards had cracks. And they obviously then were rather embarrassed about how quickly they got this person on the floor, and they're talking about all their labor problems and blah, 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 blah. And I said, if there's a crack, it will fail. So all of these boards that he just depaneled, and let's grab some from your previous production this week and check them. And they ended up eating, I don't know, a couple 100,000 boards from the last couple of days of production that was still in the building. And then we sent back a whole pile more as we found that they were all cracked. They were going to just lead to untold problems going forward. Um, but the idea is it doesn't take a whole lot of work to find out where cracks come from. Some cases are much more subtle than other cases. But in this particular one, it was an untrained employee just put online to fill a gap to keep production moving with very little training. And it was a job of just breaking tabs. And they had really no idea the damage that was causing. And they probably thought the cracking was the tabs that were supposed to break apart. I didn't really blame the kid that was hired. The quality director that had been giving me the full story for an hour and a half before we got on the line, um, that one I had a problem with. And so if you're going to run a quality shop and say that you do all this training, you actually need to do it. And I think that's pretty obvious. But even a subtle crack can pass all of your electronics testing. Capacitors are supposed to look like an open. If you do an open shorts thing, they're supposed to look like an open. And if they're soldered on the board, visually, it's nearly impossible to see cracks because they're usually very small and they're just initiated. They're just enough to relieve the strain from whatever that bending force was. But it only takes a handful of thermal cycles or power cycles for that crack to propagate across the leads, across the plates, and cause problems. More often than not, it just totally fails and goes open. So hopefully you haven't run into stories like these. And you may have, there's plenty of them out there to do this. But before I go forward, I saw a couple of notes about preventing cracking and stuff like that in mechanical stress and thermal shock. Carl, you probably saw a precursor to my slide set here. Those are common ones, but what precautions can you take? And I talked about if you're doing depaneling, do it appropriately. That's one. And Carl's mentioned mechanical stress and thermal shock. I guess mechanical stress is this bending moment of the paneling process. But what do you do in your line of work, in your world? What kinds of things are you doing to avoid multi-layer ceramic capacitor failures? Manja, Manja, and I'm sorry, I'm probably not pronouncing that right, is talking about voltage and temperature derating. Excellent. Derating your products, give them more margin. Not necessarily for somebody bending the daylights out of your board, the mechanical stuff, but for the electrical ways that capacitors can fail, derating does certainly help. Really, really does. All right. Hopefully, Banjo is not the only person doing derating. Hopefully, everybody is. So, and other techniques to do this. But let's take a look at some of the common failures. But first, a little bit about how they're constructed. Unlike the ship over there that was probably constructed just fine, but ran into hopefully not a bad capacitor. Although you can see navigation systems failing due to navigation or capacitor problems. All right, so the multi-layer ceramic capacitor has the ceramic elements between two plates. Over 3,000 multi-layer ceramics on every board. That's a lot of capacitors. Those must be big boards too. But the idea here is that the basic idea of capacitance is you have two electrodes, two parallel plates, one connected to the anode, one connected to the cathode, and a dielectric between them. And that distance and the amount of voltage that's applied is what creates capacitance, this ability to withstand the current flow. And so it's basically this barium titanate slurry is put between these metal plates, the electrodes, and then it's cured. or sintered, I think is the term they use in ceramics. It's cooked, essentially. And that sintering process has to be at the right pressure and the right amount of time in order for the ceramic to fully become that dielectric that we really expect and to have occur within this capacitor. Now, the electrodes themselves have to be the right dimensions and the right surface smoothness and all those kinds of things. Yet the ceramic itself has to be cured for it to have the appropriate dielectric properties and the ability to withstand cracking. So one of the ways I learned that ceramic capacitors crack are I should have rephrased that, are more susceptible to cracking. So a smaller bending moment or a smaller thermal shock will the ceramic that isn't cured as well as it should have been on the margins will be much more likely to crack. So part of the preventative process that we started doing was visiting ceramic manufacturers and becoming pretty versed at how they manufacture these things, all of the process control steps, and paying attention to did they actually have a stable process or not. Now, we were buying so many capacitors that we couldn't only buy ones that were certified. So we continued to do other monitoring and other internal testing to isolate and find the suppliers that really knew what they're doing. And we really paid attention when they said, oh, we're moving our factory to this lower cost area. Well, nothing will change. We're moving all the people and all the equipment. Well, as everybody here knows, yeah, right. Things are going to change. You need to pay attention. The capacitors have gotten smaller and they've gotten more layers and the technology keeps improving. All of that just makes the margin for error that much smaller. So the chance of cracking, causing problems is just going up. So paying attention to how they're manufactured, the stability of their manufacturing process, the stability and consistency of your board handling, including, and we'll talk about a couple of the ways that this happens here in the next couple of slides, all really matter. And especially like the one out there, it's Manjo's talking about 3,000 capacitors per board. That's 3,000 opportunities for failure. And keeping track of how they're placed and how they're made and all that kind of stuff is all great. Yeah, David's talking about a couple of them is the orientation, spacing to the board. I just had a call about this earlier this week or late last week, was keeping capacitors away from screws on the board. The screws that were used to hold the board down actually deflect the board more often than not. And if you deflect it enough, you can crack a component. Capacitors are a prime nail of it. Same with bed of nails. If you have too much pressure on those, you can cause deflections and cause failures. Or if they inadvertently punch on top of your capacitor, that's just driving a nail through it, basically. All right, so here's a couple of telltale signatures of cracks. If you have a diagonal crack, it goes from the end cap and usually 45 at some angle into the body. That's caused by flexing. It could be the board flex, like my famous AC/DC t-shirt guy, or it could be the bed of nails. It could be board handling. It could be misalignment of the hold down screws so that there's a slight bow to the board, on and on and on. These things are pieces of glass. They break. They really, really do. So if you cross-section these things or you do a scanning acoustic microscope and you see this kind of crack, the degree comes from the end cap to the body into the body of it, is probably a flex problem. So go look for where your boards are being bent or deformed. The other one starts similarly, but it traverses down, and I don't know if I've got a pointer on here or not, on the right-hand side is it's just a small crack initiation, but it's usually from a thermal shock. And it could be very slight and create a very small crack. If a really serious thermal shock of, say, a soldering iron, hot soldering iron, say 400 degrees Celsius soldering iron, touching the end cap will certainly fracture a capacitor. Now, they're all instructed to only touch the pad. But as these things are getting smaller and smaller, and any touch-up work, or any testing or repair work is always done by hand, and it's nearly impossible to not damage the capacitor with a hot soldering iron. So keeping soldering irons cooler, yes, it takes a little bit longer, but it significantly reduces the shock that you have. And preheating the board and the capacitor, all those kinds of tricks can help. But if you see a pattern where it's like a C, goes from edge of the end cap termination to the other edge of the end cap, that's almost always a thermal shock. Now, keep in mind that these cracks can often start just being a fraction of a millimeter long, but with thermal cycling, they propagate. And then it leads to failure. Board placement. We don't use mechanical jaws anymore. That's 20, 30 years old or more. But those jaws would clamp these things, and they're not precision devices. The dimensions on them vary because that's not critical to the functionality of the component. And so mechanical jaws assumed it was a certain length or width, and they would crack it if it were too small. We've used vacuum suctioning, and there's lots of other technology on these things. But even the vacuum technique, if it's not set up correctly to sense the pressure of attachment that it's touching the top of the board, can crack it. So think of it as a 3-point bend type cracking. Shearing the boards apart and depaneling. Some use cutting machines or router devices or kinds of cutting tools to separate boards. That again deflects or misshapes the circuit board and can cause cracks. It causes cracks to occur. So keeping them away from those areas, keeping the board dead flat, doing all of the due diligence to make sure that your depaneling, your placement, board handling, all of those things don't cause deflections in your circuit board. Any of those can do it. So let's spend a couple minutes before I run out of time talking about aluminum electric failures. So we had a case of MLCC overheat. We concluded similar depaneling issue. It was a very limited number of cases, and the product was a last time buy stage. So we simply asked the suppliers who's capacity, blah, blah, blah. Yeah. No issues rose after that. Yeah. It's amazing that it can create heat. And it really does take a right kind of circuitry that doesn't give it as much current as it wants. Because if it does, it'll heat up way too quickly and just pop apart and then go open. So they tend, not always, tend to fail safe. But if you see very hot capacitors, there can be all kinds of issues with that. But cracking is often a culprit in that. Right. Again, electrolytic capacitors have been around a long time. They were in the old test tube era, or not test tube, the vacuum tubes era. They were a component on TVs that I remember testing vacuum tubes in and wondering what these things were. And my dad said, don't touch them. Even after it's powered off, they can still shock you. And they were good sized ones in our old TV back in the 60s. But they're basically two long strips of aluminum. Usually then one of them is coated or etched with an aluminum oxide, which creates a dielectric. And then a little piece of paper goes between the two strips, and then they're wound up. And that paper is coated with an electrolytic solution, electrolyte. And it's usually a gel or gel-like liquid that goes into it. And you notice that there's this rubber sealing where the leads come out. All right. So there was two parallel plates, basically separated by a little bit of electrolyte encoded paper. It's very small, very thin, and it's wound up real tight. So they get a very large parallel plate in a very small package. And depending on how long that plate is, what the surface area is, that kind of stuff would depend on what kind of capacitance these things can do. And electrolytic capacitors can create a lot of capacitance in a small space. That's why they're used. The issue is that dielectric is a deposited coating. The oxide is basically grown on the surface of this, and it's a very rough surface. And what happens is if you get a bit of voltage spike, which occurs for all kinds of reasons in our wonderful power systems around the world, it can punch right through that dielectric, creating a short. And that's one way it happens. But more commonly is that variations in your voltage, even if you have a simple 5-volt line, it's never exactly 5 volts all the time. Right? It is going to vary. And it will have hot peaks and troughs and spikes and transients and all kinds of other things that are occurring on it. With a good enough scope on it, you can see this power is not clean. And so every time it gets up to a particular level of voltage, it chips away at that dielectric. Now, this dielectric, this oxide, is coating and uncoating is a natural part of the process of this thing. And some areas will be thinner and thicker than other ones. Well, the thinner areas are more susceptible to higher voltages. And this is the primary reason why it's so important to derate them, because you need that voltage margin to prolong the life of that dielectric material. And it's like the old incandescent light bulbs. There's a reason there's a vacuum around those light bulbs, and usually it's filled with some inert gas of some sort. But the idea is that electrode that's glowing is shedding molecules and atoms. And as it is turned off or cooled, those shedded atoms and molecules are redeposited. And it gives it life over longer than just burning through it at one point. It's much like that inside an electrolytic capacitor. That dielectric is not stationary. It's going to be moving as the capacitor takes on a charge or discharges it. And it tends to not coat perfectly evenly. Over time, say 10 to 15 years on the bigger capacitors, longer for smaller capacitors, the dielectric will eventually get too thin and will fail under normal voltage application. It's why capacitors like these tend to fail on power up, is that's when they first get applied to voltage. And if there's a weakness in it, it's usually that power on voltage is what will punch through and cause it to fail. But it's very, very common. Preventing it is really getting good suppliers, but also doing derating and making sure that these systems don't get lots of ripple current, lots of overheating, all of these things that would exacerbate the breakdown of the dielectric. So that's one way that they break down. And there's probably a dozen contributors to this, but I think understanding the sketch of how this occurs gives you something to look for as you're doing failure analysis or vendors association. The other kind of failure is leakage. If that electrolytic solution evaporates or vaporizes or leaks out of the can, then it won't be there to do its job of keeping these two plates separate. And then it generally shorts out. And a short then leads to heat, and that's a problem. The other problem is that the electrolytic solution itself is pretty caustic. I think that's the right term, but it's conductive is the key thing. And you don't want that on your circuit board. As that flows around and Murphy's law comes into play, it's going to find a place to short and create more damage, as this image would illustrate. The most common way electrolytic solutions dissipate or go or come out of a can, besides mechanical puncture and things like that, is it's just normally evolved off. That metal can and the rubber gaskets is not sufficient to keep all of that electrolytic solution trapped, especially as it volatilizes. And it will seep out. So if you have an old radio that's 40, 50 years old and has great big capacitors in them, the likelihood of those capacitors having their electrolytic solution still intact is very low. So be very cautious turning those on because they very likely could cause a problem, like exploding. More commonly, though, is that it dissipates over time. And they typically, the bigger capacitors have a life of, say, 15 years, give or take. And that's normal. That means they have normal temperatures, normal types of electronic or electrical forces on them, normal voltages, not a lot of spikes or other problems breaking down the dielectrics, but they wear out. Now, it can happen much quicker if there's damage to that rubber gaskets. If there's mechanical damage to those, they're placed incorrectly, they're overheated and burn up the lead too hot and open up a channel for the dielectric or the electrolytics to seep out. So plenty of ways these things can fail. Usually it deals with the electrolytic solution or the dielectric. There can be other problems. There can be contaminants. There can be all kinds of stuff. The issue I've seen most often with these cans is that they're installed too proud, so that the two very thin leads are supporting the mass of the entire capacitor, say a half inch to an inch off the board. And it's much more practical and much more likely that those leads were not designed to do that, to support that weight with any kind of vibration. So make sure your capacitors are mounted flush to the board and as tight as they can so that they don't vibrate and break those leads. That's the most common thing I've seen. But over time, they will fail. And when they do, they usually make a mess. So a couple of things to keep in mind there. So I'm going to say that I didn't talk about all the ways these can fail. I know Bert and Carl and a handful of others are talking about these things. I see a comment about ripple current. Yeah, ripple current is this fluctuating waveform that the capacitor sees, and it doesn't know whether to charge or discharge. It's kind of wavering back and forth, and it creates a lot of motion within the capacitor, and motion is heat. So ripple current is going to happen. It's always there, and you can derate for it. But the electrical engineers need to make sure that it's minimized, especially around electrolytic capacitors, because it does create a lot of heat, and that just accelerates, much like what we do on purpose in accelerated testing, the time for their demise. It's one of the simplest things to do is make sure you have good designs, minimize ripple current, and derating, the voltage and temperature derating, stuff like that. So I just scratched the surface. A handful of stories. All of this is from my experience of things I've seen in one form or another, things I've learned along the way. And if you ever run into, and one of the sources I cite in the here was by John Maxwell, and he's been, I don't know if he's still active anymore or not, but he was like the go-to person about how capacitors fail. especially multi-layer ceramics. And at one point, I know he was a consultant doing nothing but capacitor failure analysis and design techniques and so on, selecting capacitors. He was the go-to capacitor person. I never aspired to do that completely because even though you can make a living doing it, just working on capacitor failures, I found that kind of boring. So I, worked on inductors and worked on silicon devices, worked on mechanical devices, all kinds of other systems, which keeps it more interesting. But having a good, solid understanding of constructions, where the weaknesses are, what are common, what is uncommon, how do you prevent it? Not just for capacitors, this is just an example, but for every component and material that we're working with, will go a long way to help you and your organization create reliable products. So hopefully you can see that and make a difference in your work. So I'll wrap up here and ask if you have any other comments or questions. Thanks for all the comments in here and all the ideas for future, couple ideas for future webinar topics. I'll get into those. Yeah, David's talking about ECAPs, all about temperature. I think ripple current's another big taboo thing for it. So don't put your junior engineer on designing that board unless they know what they're doing around ripple current. But also pay attention to manufacturing processes. If you don't cure the ceramic right, it's going to cause a problem. If you don't wrap and seal the electrolytics correctly, they're going to fail. Yeah, there's all kinds of forces. Yeah, and turning all at once full power, that's a tough one. It's going to really have that onrush current. It can create a lot of havoc unless it's really taken care of. All right. So I'll close it out here. I don't think I have another slide after this. Yeah, I do. I rarely get to this one. So thanks. Thanks for attending. Thanks for all the comments and stuff like that. Now go make capacitors more reliable. That'd be a real benefit.